Okay, so very good evening and welcome to this episode on tensor fundamentals. My name is Shaunak, and uh, we will be looking into tensors in today's lecture, but not only one lecture would do. It might have to take a few more lectures to understand the basic concept and idea of tensors, but it is always a very good, concept. Look at the idea of tensors first of all, and then we will go into. Sorry for the noise because I'm just checking whether my audio is working or not because few minutes back it was actually not working. So I need to check in whether the audio is fine or not. So I'm just checking on that part. Yeah, I think this is absolutely fine. Okay, so in order to start with tensor, very good evening. I just came from the college, so I'm just having a cup of coffee. Hope you won't mind. So first of all, whenever we talk about tensors, the basic idea that comes in our mind regarding tensors is that tensors are indeed very difficult. I mean to say tensors are very difficult in order to understand. Tensors are very difficult in order to comprehend all of those stuffs, especially in terms of tensor calculus and how things would do. So it is not that today I am sitting down and talking about tensors to all of you, but yes, I have done a lot many videos on tensors earlier, and here is a list. So what you can do, I'm so sorry. What you can do is that you can go to my playlist in tensors. Now, mind it, these are my old videos when I was using a pencil, and a sketch pen and a white paper to look, but these are good videos. I mean to say they are although I would say they are mathematical in nature, but it starts directly with the mathematics. So I did not get that time to explain because it was a new channel. I was hardly aware about the technology, so just pen and a paper and a camera I used to do. So but these are very good videos which you can definitely look into it. I think it will be useful because all of them are related to tensors. So these are videos which relates to the mathematics of tensors. However, I have already started dealing with a new part of mathematics, and these are separate videos, and I will be continuing with the learning of the mathematics also. Now, before I go ahead and explain you specifically about tensors, now this is a very serious topic. I mean to say there cannot be any ifs and buts. It is something very serious, something very modern, and something which carries a lot of prospects in terms of career. So I want to take a absolutely step-by-step approach, and I want to tell you exactly the origin, the problems, and then we will come to tensor. Although in my college today I was reading something very interesting about Minkowski space and special theory relativity, and there I found an amazing concept of tensor. This is, I'm going to say, this is not written in the book, but this is something which I found it out. I will share with you. Okay, so you need to understand one thing. You might say that why do I always go back to the history? Now I always go back to the history because what I am teaching you, what we are understanding right now, has its relevance in the history. I understand you people are going through a lot of examinations, undergrad, grad, or competitive exam. So you really don't have the time to explore the history. But here I am. I've got enough amount of time to teach you and make you understand the basic roots. Unless you understand the roots, the concept of tensors won't be clear. So here you see it comes from the Latin word tender. It is not that softness, it means stretching. It means tightening of the muscles. So it has to do something with stretching and pulling. Now, see, for example, on a sphere, I get a kind of a, any kind of a data. Say any kind of a data. Okay. Now, that sphere, when I stretch it, now you might say, what is this stretching? Mathematical stretching, it is a physical stretching. I will come to that. When I stretch that, let us say, for example, physically, the information around it gets stretched. So a sphere becomes what is called an oblate spheroid. Okay, Anik, thank you very much. Thank you for your comment. So this actually gets stretched up. Now, wait, that is something I would again take a step back and tell. This stretching of something is a very important concept of differential geometry. because tensors actually starts, the history of tensor is not with Einstein. History of tensors is much back to with Bernhard Riemann. I will tell you the name. You all know, I call him the granddaddy of mathematics. It is Bernhard Riemann. Okay, so Riemann actually coined the term manifold during that time. Yes, Salman, very good evening. Good evening. So Riemann actually coined the term the tensor. But actually, he coined the term what is called manifold. Riemann actually coined the term manifold. Tensor was done by somebody else, I will tell you. But it is much year back to Einstein. So remember that it has nothing to do with Einstein. Einstein did not knew about tensors. It was Marcel Grossman and others who taught him tensors. I have repeated this in numerous videos. So the basic concept is that this stretching, that means the space time or the surface where things are happening, say for example, this gets stretched, right? So once this gets stretched, there is a kind of a deformity which happens. Now note, when I talk of deformity, it has also to do with topology. Because in topology, for example, I can bend this one, I can do this one. That means this bending, twisting, etc. has to do with the surface on which the entire physics is happening. Are you getting my point? If you don't understand, please put it in the comment box. So bending, stretching, everything happening on the surface. That surface is called a manifold. I will come to manifold later because manifold again has got a huge understanding. Now that means this stretching, bending, etc. is causing a distortion in terms of the data. What data? I am not telling you right now. Data, any amount of information, it is getting distorted. It is changing coordinates. It is getting transformed. It is getting twisted, whatever it is happening. So question is that when I tell you this particular part that it actually stretches, that means a set of components, functions of the coordinates of any point space that transform linearly. Okay, what is a second rank tensor? Okay, you have to wait. There's a first rank tensor, there's a second rank tensor. These are actually dimensions. I will show you. I mean to say, I really cannot tell you anything which has got 0, 1 and further dimensions is called a second rank tensor, right? So you need to wait because I have to show you and it is already here. Okay, when we are talking about of a sphere where it is replaced, what kind of information is attached to this? Coordinates? Absolutely. You are very right, Dhruba. Now, also, I would like to tell you, Dhruba, coordinates definitely is being changed. But remember, in differential geometry, when we are talking, we will take it to other area, that is topology. We do not call them as coordinates. Coordinate, the term coordinate itself is very restricted to Cartesian space. Okay, are you getting me, Dhruba? So coordinate, the term, I mean to say, you can definitely tell coordinate, why not? But it is something which is very specific to Cartesian flat space. Okay, here we called it as a manifold, right? Padmanabhan versus Winberg, who have best books on GR? Goat, I would really request you that this particular we are actually trying to learn. We all are trying to learn tensors. So both of them have great books on GR. Both of them are equally great and brilliant. So it is not that who have best book. Both of them have great books. Steven Weinberg's book is more towards cosmology, and Padmanabhan's book is more towards the mathematical understanding. So Dhruba, you understand my point. Technically, we should call it as a manifold because coordinates will now being changed. The term will change. But yes, it in terms of coordinates, it won't be coordinate. It will be a kind of a bending of the entire structure. I really cannot tell you like that. But yes, intuitively, you are very right. Okay. Next, what we see over here is that these are few of the features. Tensors, Atharv, Kadav. Yeah, hi, hello, how are you, Atharv? A very good evening. So tensors are vectors which have not a single direction, but they rather point in all directions. So you see a cube. So in vectors, what do we see? We say that there is a magnitude and a direction. But here we need to say which side, which part of the cube the things are occurring. And this will come more easy when we talk about stress tensor and Cauchy stress tensor. Just hold on. Tensors have properties of both vectors and scalars, that is area, states, etc. And A tensor is not a scalar, a vector or anything. It is just an abstract quantity. Yeah, this is something important. Although in general theory of relativity, once we will start learning metric tensor, it will say it gives in a vector and produces a scalar, something like that. But actually, it is true that it is a very abstract quantity. And the tensors are actually what we called geometrical object that describe the linear transformation. Here is the thing, what Dhruva was telling, that sir, is it a coordinate transformation? Let us assume, Dhruva, whatever you're telling is right. So when the coordinate transformation will take place, the information should not be lost. The laws of physics should be same. The vectors should be invariant. But what will happen when we transfer from a sphere to oblate spheroid, from a flat space to a curved space, whatever we are transforming, that transformation should have a set of rules. And tensors would define a set of rules through which we will understand. That means we need to form a set of rules or frame a set of rules through which the transformation becomes easier. Okay, so you can imagine something like this. Visually, it will be easy for you. A tensor is like a flexible data structure. It can store numbers in a grid of multiple dimensions to organize and manipulate data in a very complex way. Now, here is something, I don't know whether you are aware about that. Maybe Salman, Atharv, those who are maybe Goat or Dhruva, you are aware that Google has something which is called a tensor flow. You go to Google and type out tensor. Even in YouTube, you type out tensor. Something which comes up is a tensor flow. Have you seen that? You can put it in the comment box. I would like to interact. So TensorFlow is something, a kind of a programming. It is a kind of a Google's own production. But the more or less the idea of TensorFlow in terms of programming in Python, etc., is the same thing. Huge amount of data, huge amount of data, which otherwise cannot be stored. Python library, yeah, absolutely. Salman is right. This is a Python library, right? So huge amount of data is being stored in TensorFlow or in tensors. And you see, Salman might be knowing, we use Python to use that tensors dimensions in order to do the programming. So the root is the mathematics. I mean to say, you cannot deny. Here we are using manually tensors. We are doing that. They are using programmatically. But tensors, in one way, it is good that even if you're not doing physics or mathematics for the future, but learning tensors will take you into the data science or this type of programming, which Salman is telling, Python, etc. But the concept is the same. Only the language will be Python. In here, it is a physics or mathematics language. So tensor is very important in your future learning also. Yeah. So I am right. Yeah. Because I really don't know, and I always learn from you people. So if Salman is telling that he's into computer science, maybe he knows that. So TensorFlow and tensor is very important. So here you see a tensor is a mathematical object that describes a multilinear relationship between sets of algebraic objects related to vector space, and tensors may map between different objects. That means from here to here, if I'm transferring something in a multilinear way, that is what is tensors actually. Now you see, if you watch my video, what is abstract algebra? What is the power of abstractness? You see, more we move from concrete towards abstractness, things become better. Things become tighter. Things become concrete. It is easier for us to define an abstract object. Although mentally it is very difficult to understand, but things become easier because we are doing something abstract. Tensor is also, that is why it is called a mathematically abstract object which can store. So why I am constantly telling you about tensor, so that before we jump into the mathematics, you all are aware, more or less get an intuitive idea into tensors. I know you are busy, your professors, etc., won't take that time to go to that root level which I am doing. No, I am not boasting, but I'm just telling you that this level of understanding is also required. If you do this level of deep understanding, the mathematics will become easier. So that is why people say maybe my videos are going much deeper. So that is why I've tried to explain this. Okay, now I come what is called the important features of tensor. Okay, just a second. All of you can hear me. The audio is clear. Please put a yes or no. There's a problem with audio, so I'm just asking you. Okay, so here is Goat's answer. that what is the rank of a tensor. Okay, so tensors can be of any rank, which means they have any number of dimensions. Now you see, okay, thank you, Salman. Salman has been very participative. Thank you very much. So you see that ranks of tensors are actually in one way, which means are the dimensions. Immediately the thing, sir, can you please tell me what does abstract tensor? No. It is not an abstract tensor physics core. What I am saying is that you go to the previous slide, you will see I have written that tensor is a kind of a mathematically abstract object. Tensors may map between different, and you see tensor is a mathematical to discuss multilinear relationship between set of algebraic object. Tensors may map between different vectors such as vector scalars, etc. So we can say that it is a kind of an abstractness. It is a kind of an abstract mathematical object, right? Which is very flexible. If it is not abstract, then flexibility will become a problem. Then we have to follow this rule, this rule, this rule. So abstract algebra, group theory, ring theory, all these things, even tensors, are abstract because we can go up to any dimensions, right? I hope you understand. And I don't know what is abstract tensor. If you want to mean something else which is called an abstract tensor, maybe. I mean to say I won't be able to tell you that. This is the rank. So rank or order, this answers Goat's question. The rank of a tensor is corresponding to the number of indices. For example, a scalar has rank 0, a vector has rank 1, and a matrix has rank 2. Okay, it is clear. Okay, thank you very much. Okay, so Goat, you got it, that a matrix has got a rank 2. So now immediately you see, I was talking about abstractness. What is the power? I will come to that. Tensors have got ranks which actually speaks about dimensions. What requires extra dimensions? String theory? Yes. General relativity? Yes. Maybe quantum mechanics, maybe some other areas of physics. So if I get a kind of a mathematical model, this is very important for those who wants to go into what I would say pure mathematics. You need to understand that, otherwise you won't be able to frame what is called a mathematical model. Forming a mathematical model means that you need to form its abstractness. The moment you see that indices, that means what is required for indices? These are the areas which are required for indices. That means, is string theory using tensor? Is general relativity using tensors? Automatically questions comes and you get the answer. You don't have to come to me. I'm trying to make you independent. I mean, yeah, it's better you come to me, then we can have classes. Okay, the shape of a tensor indicates the number of dimensions which I've got. Components are actually, each element of a tensor is called a component. And transformation rules, obviously there will be transformation rules which will allow the coordinate transformation. Now you see these indices which I told you, I don't have the Jamboard. Next time I will come a little bit prepared. I will immediately share the screen. This mu nu, you know Einstein's field equation, you might have seen in my videos. So this mu nu are indices, and these indices are coming where? From where? These indices are coming from the dimensions which are actually associated with the tensor. Okay, sir, n to n order matrices also rank to tensor. No. If it is nth dimension, then it would be rank n tensor. Got it? If I consider the tensors indices to be the rank of the tensor and the dimension, so 1, 2, 3, 4, 5, then n, then it is called nth rank of tensor. You will see this book, Prasun Kumar Nayak has got a lot of mathematics in nth dimension tensors. But that I mean to say, it is good that Salman, you have asked this question. That means you're thinking. That means what is beyond 1, 2, or 3, you can generalize it and make it an nth dimension tensor. So we are clear with the rank, we are clear with the shape, we are clear with the components, and we are clear with the transformation rules. Yeah, this is my usual diet after coming from college. One hot coffee. That's it. Okay, here you see this is what is a physical, schematic diagram. You see scalar, rank 0. Goat, I think now it becomes clear. Rank 1 tensor, 1, 2, 3. Rank 2 tensor, this. Rank 3 tensor, this. Rank 4, 5, 6, etc. Physically, it is not possible to show because it has got more dimension. But overall, it is that what you can understand. And you see, I would like to take 1 second and explain you this thing. You see these points, these lines, this. Now, what happens is that now you see the mathematics of tensor, it sounds to be complicated. The reason it is complicated because you have to explore now the this side, that part of the cube, the stress, etc. So I mean to say, lot of components and areas needs to be summarized. So there is a vector, there is a magnitude, there is a direction, on which plane, on which dimension, on that dimension, that plane, and this stress is happening. So I mean to say, the language of tensor is carrying lot of things in one point. So the mathematical equation of tensors are like upper indices, lower indices, upper this, that, up on the top. So why? Because these are all trying to make the mathematics, the dimension, much more portable. I repeat the word, much more portable. Portable means in one mobile you will find a calling, a video call, a WhatsApp, a television, maybe your radio FM, everything together. Now, don't you think that assembling today's cell phone will require a lot of time, will require a lot of patience? Assembling a computer, assembling even a cathode ray tube, smart TV. Same happens with tensor, because now you see in this picture, so many things need to be put up in one specific equation. That is the tensor equation. So the next time when you see the tensor equation, just try to visualize why it is so much complicated. It has got indices, nothing, because it is just like a mobile phone. It is trying to assemble a lot of features in one. Earlier mobiles were very easy. Can we say it is more accessible and precise? Yeah, absolutely. It is more accessible, it is more portable. I'm using the term physics core, portable, because otherwise for a television we have a TV, for a video camera we have a camera, with a mobile, three different things are put together. That is why it is called accessible, yes, and precise. Absolutely, absolutely true. It is much more precise. Okay. So sorry. I don't know why this mouse. Okay, here you see, this is, I will elaborate on that, but just have a basic understanding. This rank, this is a tensor. Don't ask me what is sigma 11, sigma 12. I will explain it that later. Maybe you people might, some of them you might know. So rank of a tensor is defined as the number of dimensions of that tensor, and the shape of a tensor represents a size. Now, if I say sigma 11, the first one keeps track of the plane the components acts on. Components means whatever, it can be stress, etc. Which plane, which part of the plane. And the second one keeps track of the direction, left, right, up, down, etc. Now you see, I will show you in the next day, it will become more interesting. Einstein's field equations, or the metric tensor that we use, that got 3, 1, 1, 1. That means the first one would be the plane on which is acting, the second one would be the direction on which is acting, third one is on which dimension it is acting. So that is why you see, then we have to expand that, and it becomes cumbersome, it becomes huge. But the basic idea is that you need to understand, all of you, that without that we are also helpless. Without the usage of tensors, it won't be possible for us to what physics code told, assimilate so many things and make them accessible and precise. So that is why we need those things. So this is a kind of an understanding that so you might say that are tensors generalizations of vectors? Technically, no. Tensors are not generalizations of vectors. Tensors are not generalization of matrices. They are something different. Technically, no, but for the sake of understanding, yes, it looks like a matrix, 1 by 1, 1 by 2 matrix. So it looks like that. So why don't we take it forward from there? Okay. Here you see what I'm trying to tell, that from a flat space, that red one, which has got a kind of a data, say for example, it moves into the curve space. Somebody was asking, yeah, it has got a transformation in terms of coordinate. Okay, so how do we measure this? How to keep things measurement, how to keep the measurement invariant in spite of the coordinate changes? How will I make those things same without the changes? Object is stretched, and here you see this one is rotated to this one. Now you see, do you see, I mean to say, Salman and physics core and those who are watching, do you see that this concept, that how do we keep things invariant, something is close to Einstein's formulation of special relativity? something which is very close to Einstein's general relativity. Can you relate that? Special relativity tells that the laws of physics will be invariant and the speed of light is constant, right? So why is that we need that the laws of physics to be invariant? Why it is that in general relativity, even when we are moving from flat space to curved space, we need to have the vector to be measuring in the same direction? Why it is so? This is the idea that it is not only for tensors, this is something more deep, that any physical any formulation of physics or mathematics that we do not want to disturb the basic thing, that is the laws of nature. The measurement has to be the same. So now you see, you will all be able to answer yourself. You don't have to ask me. Now you see, you will immediately understand why tensors are very much required in Einstein's relativity, why tensors are required in electromagnetism, why tensors are required in stress energy momentum tensors, all of this. And you might, maybe Salman or physics core, um, covariant and contravariant retains. Yeah, Rakesh is one step always ahead. So yeah, covariant and contravariant, what it is, we will come to that. But yes, it is a right point that it retains that. That means that in order to formulate a physics or a mathematical theory, we need to find out something which is very invariant. And for that invariance, there has to be new laws, new frames, new matrices, etc. So that is why you will see, I don't need to tell, you will yourself understand. Okay, I will come to this later. Can I get the PDF of the slides? I will come to you, Salman, later. No problem. So the laws of nature would be invariant. Okay, now you see that from flat space, we are moving to curved space. So consistency across the frames of reference. This point on the right-hand side is very important. The different observer may use different coordinate systems to describe the same phenomena, but the laws of transformation of tensors ensures what? They ensure that the physical quantities described by tensors maintain their meaning and relationships. Don't feel bored that why constantly I'm repeating on the same thing and same thing. My teacher says that it is good because once you constantly repeat on something, the students understand more. Repetition is one of the aspects of learning. You repeat, you repeat, you repeat, you never forget. But if you skip through that once, it is not done. Especially in kind of a fundamental learning like physics and mathematics, you need to repeat and you need to give various examples so that you don't forget. Do you all agree to that? Right. So that is why it is coming. So general relativity, the theory of general relativity, which describes gravity as a space-time curvature, requires tensors. Why? Because the transformation is there. Because the transformation is there. And this transformation will be done by what? Is done by tensors. Yeah. Is the change of dimensions time dependent? Change of dimensions time dependent? No, I don't get it, because this would require a lot of questions to you also, Dhruba. I mean to say, what do you mean by change of dimensions? If I am changing from a flat space to curved space, obviously, in case of a Cartesian coordinate, I will consider time as dependent variable. I mean to say, I cannot consider time as independent. The moment I take the relativistic effects, then obviously, I mean to say, special relativity, we are not taking into general relativity. Obviously, time and space are not different things. So how can we tell it is separate of a time? Are you getting my point? I mean to say for example, I use Newton's laws of motion and I try to extrapolate that to tensors, which we can. In that case, time will be separate. But also, you see, Dhruba, there is a problem. The problem is that the moment we try to include Newton's laws of motions to a tensor, which is one single formulation, we have to include time. And the moment we try to include time, Newton's law will fail. Why? Because time and space for Newton's law are different. That means you are trying to compare an orange to an elephant. You cannot do that. That is the limitation. I hope you are getting my point. So whether it is dependent and independent, it depends upon what system, what coordinate system you are following. If you're trying to hypothetically take Newton's law of motion into tensors, then you have to take time separately. But the moment you take time separately, tensors won't happen, because tensors mean that everything should be, as pointed by physics core, accessible and precise. I mean to say things like that. Are you getting my point, Dhruba? It's a good question, but you also need to think a little bit, deeply. Okay, so coordinate difference and tensors allow physicists to this. Okay, here you see this is a very important diagram. Now you see a person is throwing a ball in one frame of reference. I hope Dhruva part is clear. You can say me yes or no, and please do interact also. I mean to say that looks good. Now this frame of reference is being rotated. This is rotated over here. That means the throwing of the ball or the event won't change. Okay. If it is extended, the x and y axis, do you think the throwing of the ball, etc., would change? No, nothing. So events will be measured in the same way in all frames of reference. That is why unknowingly, without knowing tensors, Einstein told that the general laws of nature must be identical equations to all their systems, whichever way they are moving. That means independently, there was a need for development of tensors because whatever the frames of reference were happening. Now, here is a very intelligent question which I might ask you. Will you be able to answer? You can interact. My question to all of you, those who are watching, is that if the events are occurring, should occur in the same way in all frames of reference, forget about general theory of relativity. Do special theory of relativity include tensors? Because there also we see that if things are happening in this frame of reference, the same thing will happen in this frame of reference, even it is accelerated, rotated, or the observer is moving faster. Again, let me reframe my question. If we need to observe the physical laws of motion same independent to all observers frame of reference, whether it is running or doing anything, does that mean that special theory of relativity also will include tensors? But whenever we talk about tensor, it starts with Einstein's relativity. What is the catch? You tell me, you decide, and you talk, and you let me know. I will proceed with this part of the class today. So what we need is that this space and time is now taken up in a lump. I will explain to you because I'm coming up with the webinar day after tomorrow. It is in a lump which tells that space plus time is equal to space time. So the universal laws should not depend on any particular coordinate. Very true. And we need a tensor which is called a metric tensor that describes the distances, how are measured, and space-time in terms of specific coordinates. Here is again a question to all of you. Let me know. I mean to say, otherwise the learning will be all my lectures, you all are listening, etc. My question is that here in general relativity, we are telling that metric tensor would describe in a space-time certain specific coordinates, etc. Now, the causal structure, that means angles, etc., are also was measured in special theory of relativity, right? Don't think that the teacher is asking you a question, but just a kind of an interaction so that you find. So, what is the component in special theory of relativity which describes events? What is the component? What is the mathematical structure of special theory of relativity that describes events and happenings around the space, etc.? What is the component of special relativity that describes the events? In general relativity, we know that it is described by Instagram user. Okay, so in general relativity, we know that it is defined by metric tensor. But if metric tensor is an extension of something, a question mark, what is the component? What is the mathematical structure? You all know, try to think. I am making you think so that you get the answer yourself. Absolutely right. Absolutely right. Light cones. Light cones, which are basically defined on Minkowski space, are basically a mathematical object, or whatever we can say, that describes the future light cone, the present light cone, and the past, present, and future. Now you see what Dhruva has told, this light cone, this is now being extended into this metric tensor component. Dhruva, are you getting my point? I think you are absolutely on the right mental track. So now the question is that this light cone, it is being extended to metric tensor. And whenever we are measuring space-time intervals, we use delta S square. I don't have the, very sorry for this, I don't have the Jamboard ready. Delta S squared, which will be equal to what? Minus c square t d square plus dx square plus dy square plus dz square, and so on. Here also there is a tensor. In the space-time interval of special theory of relativity, there is also a tensor. I mean, it's not a tensor, but something which is trying to make use of the tensor. Okay, I won't make you wait for that. I know you're all tired. This is called the space-time interval. The minus c square t d square. You know how space-time interval is calculated. That minus c sign before the time actually gives the invariance in terms of space-time interval. I will show you next day mathematically that what if we do a Minkowski metric with a minus sign, without a minus sign. If we do without a minus sign, that means c squared dt d square, what will come upon is that what I am observing, Dhruva is also observing. That cannot be. Because if Dhruva is accelerating, don't mind, I'm just taking his name. If Dhruva is accelerating beyond my, I mean to say in an accelerated frame of reference, and I am sitting, Dhruva's light will have a time dilation. That means there will be a difference in terms of time. And this difference in terms of time will make the delta s square, that is the space-time interval, invariant. No change. And that is what we are striving to do in tensor. Are you getting my point, Dhruva and Salman Khan? Am I going too fast? This line of Einstein, that the general laws of nature must be expressed identical equations relative to all other systems, whichever they are moving, this is what is basically called the invariance. You yourself do the mathematics. I will show you next day, very interesting, that if I remove the minus c, then whatever I am seeing and Rakesh is seeing and physics core is seeing, it is all the same. That means that gamma, that Lorentz factor won't come and there is no time dilation. And how that can happen? Because special theory of relativity talks about time dilation, the Lorentz factor. That means, you see what I was talking and asking to all of you, that in special theory of relativity, there is also an attempt to make the laws of physical laws invariant, and that is the space-time interval, which is measured by light cone, as Dhruva has rightly told. So the light cone is being used in terms of special relativity, keeping minus sign, so that the time interval, if it is increased or decreased, will maintain delta s squared. That is the space-time interval. Space-time interval cannot be disturbed. Space-time interval should be the same. That means, yes, in special theory of relativity, we can also use tensors. And I will show you that the Maxwell's equations, the relativistic Maxwell's equation, are also using tensors. F mu nu, right on the top. Okay, now I was asking this question that what if special theory of relativity can be extended? Definitely it is extended. Now, who was asking this question? Let me go back. That was a very intelligent question. I think, is the change of dimensions time dependent? Dhruva was asking. Now here you see, Dhruva and others, that whenever I am using relativistic Maxwell's equation, I am using tensor. But prior to that, there was no need for tensors. Why? I'm asking this to everybody. Why? Because whenever we are using relativistic Maxwell's equation, I am using relativity. And what do I mean by using special relativity? I am using space and time together. It is not an independent component. So Dhruva, I hope you are getting now a much more deeper. Is the change of dimensions time dependent? Depends on which level of physics you are using. So Galilean transformation are not relativistic. Then that means in Galilean law, we cannot use tensor because we cannot merge things together. But in case of a relativistic Maxwell's equation, space and time are not independent. They are all at once. But remember, the tensors can also be used in case of a stress. And stress evolution is something different. Anyway, I'm just going a little bit hayward. So you see that in transformation rules of tensor, it is the events should be the same. That means in special theory of relativity, these light cones are extended to metric tensors. Light cones are using the invariant nature, that is the space-time interval. This space-time interval shows that whatever be the laws of nature, it is moving up, down, etc. The space-time invariant will be the same. It is invariant. And what takes the responsibility to make the space-time interval? The minus sign. The minus sign will include the Lorentz factor, which is causing the time dilation. That means what I am seeing and what physics course or Salman or 13 other people are seeing is not the same. If it would have been the same, that means there is no difference. That means the entire special relativity will fail. I hope I can make it understand. Anyway, many things are coming at once. Okay, so where do we go from here? Here you see, this is again this 0, 1, 2, 3, 4, etc. Tensors generalize the concepts of scalars, vectors, and matrices to higher dimension. Again, that is a very wrong definition. I'm sorry for that, but just to make things easier. Tensors extend the concept to any number of dimensions, and the curvature of space-time is described by the metric tensor, which is a rank 2 tensor, and it is how the distances and angles are measured between space-time. This actually brings to Dhuba's point, light cones. That means what we are seeing now, or what we will see in the next class tomorrow and day after tomorrow, this is nothing but what is called are the light cones. Now, if you really don't have gone through light cones, space-time interval, go through that, repeat that, because I am not going to teach the mathematics of deriving space-time interval. I will be doing something much more deeper. I will show you the analogy between light cones and metric tensor, and why light cones are failing and where the metric tensor takes it up. Remember, and also look into the minus c factor, which is very important. I have seen students asking question, why it is minus c? Okay, I will just quickly go ahead with this. This is a very good knowledge I think you should acquire. Remember that tensors were actually started when we started studying crystals. And why crystals? Because crystals have different type of shapes. They are weird in structures. They have got different sides. And when we cut, when we put stress, all those mathematics takes place. So all these, crystal structures, when I take them and extend them, you see these are all different lattices of crystal structure. And we use a lot of lattice mathematics also in crystal structures. So here it is not only important about the direction, but also on which plane it is occurring. So the generalization factor again starts from crystals, because whenever we are studying crystal, we are saying, no, vectors are not occurring. The linear transformations are creating a problem. Are you getting my point? Yeah. So here it is. So when you heat a kind of a glass, simple glass, it will expand in the same amount in each direction. This. But when you heat a crystal, the expansion of crystal will differ depending on whether one is measuring parallel to the x-axis or parallel to the y or b axis. Elasticity and thermal expansion cannot be expressed as scalars. This is important. Elasticity and thermal expansion cannot be done through scalars. We use tensors as a tool with more and complex situation, because single crystal properties are important, because it helps us to understand the bulk behavior of rocks and others, etc. So this would be all for today's lecture, and tomorrow also we will continue with this one. In the meantime, whatever I have told you, please have a what I would say, take a note of that. If you're really serious with your study, I'm going to say, just go through that, take a note whether you have understood. If you have question, ask me tomorrow in the class and we will expand with that. We will start with why we study tensor and those on. But remember, any mathematical theory, any mathematical new idea that a scientist or a mathematician is willing to give is not to make life complicated. So no tension with tensors. Okay, tensors without tension, we can tell it, right, Dhruva? Is it a good word to tell? Tensors without tension. Let it be a class title, tensors without tensor. Will you continue quantum mechanics separately? Yes, absolutely. Dhruva, I am actually I am into so many things. Anyway, that is a very personal issue I don't want to discuss. I am trying to create a complete class with quantum mechanics, quantum field theory, tensors, and classical mechanics, and general relativity, obviously. Now, my question to all of you, those who are listening, please help me out with something which I'm asking you. In YouTube, there is something which is called a podcast. Okay, now I really don't know. I think podcasts are basically interviews like I am taking with different people, scientists, etc. My question to all of you is that, can I move those videos and lectures with those people coming up with Dr. Debanjan and Dr. Sudeshna, with Professor Shantan, can I move those videos to the podcast section and leave the live section only for classes? I don't know whether it will affect my video. So if you really do have an idea, anybody, Salman, Dhruba, or whoever is watching, please let me know later in my email or through my WhatsApp. Can I move the videos of interviews to the podcast section of YouTube? And I can use the live section only for our classes, because otherwise all the videos are getting confused. Somebody is telling, sir, I don't know where it is, and somebody is telling where it is. So I want to create a playlist and a schedule: Monday quantum mechanics, Tuesday tensor calculus, Wednesday general relativity, Thursday a rest day, Friday. In this way we create a complete class, and we start with that December onwards. So I need to know, if you can please tell me, that this podcast section, can I remove this? Yeah, I can create a specific playlist, that I know, Dhruba. But the thing is that podcast means basically interviews. So those things which I have already taken in the interview, if I move it to the podcast section, sir, your teaching is unique and more effective for everyone. Thank you. So what I'm asking you, Dhruba, is that if I move those things in the podcast section and use those hashtags, because I want people to know more. So if I put it in the podcast section, will be people able to find that, okay, interviews are in podcasts and classes are in live section? My question is that, because interviews will continue. Again, I've got somebody coming for quantum computers. So how can I make those interviews move to a section and put those hashtags so that people can find, if I go to this channel, all the interviews are here? Okay, you are saying yes. Okay, fine. So then let me have a look. I will put all of this. Okay, Salman is also telling yes, sir. Yeah, you are young people, you know much more than me. So I will put those things. Oh, physics code is also telling yes, but put that on thumbnails. Yeah. I will put that. I mean to say, Dhruva, you are telling that podcast with Dr. Iqbal from University of Cambridge, something like that, right? Yeah, I think if you're telling that, we can put that. So podcast will be put in the podcast section, and let the live section will be going on with live classes. And I think it is better to make a schedule, isn't it, Salman and Physics Core, that on which day I will be speaking on what, right? I think that will make or it might create a negative impact where people might not be interested, might not come to the class. Anyway, I think physics, people were interested in electromagnetism, classical thing, right? Yeah, Dhruva is telling exactly. So I think it is better to make a schedule. So those who wants to learn general relativity will come on that day, or maybe those who are interested in both will come on both the days, because it is, I don't mind. I always like you to participate more and more, and I'm requesting all of you to please share the videos, because these are something I understand today that it is very unique. I mean to say, very detailed and different discussions, etc. Share the videos to your friends, colleges, universities, because I want people to learn more. See, it is just a 15,000 people have got millions of subscribers. I don't know how in I see 10 million, 12 million subscribers of food bloggers, and then people who are touring around Kulu Manali, etc. I don't know how do they get 20 lakh, 30 lakh view. Anyway, so that is a different issue. So fine. So I would take a rest today, and tomorrow we are continue with the tensor part, right? And we will end at one part of the fundamentals of tensor. Then I will go to the mathematics of tensor. I think that what my wife was also suggesting, you all are just like my children, that more than the videos, I think live classes are becoming more important. Because what I do in videos is all okay, but again, when I'm doing the classes, I can find out certain things. Well, tomorrow I'm going to show you the space-time interval also. Can I get a PDF of these slides? Salman, I don't have PDFs actually. These are actually all videos. Okay, so if you want those, let me know. I am actually, I had a website called physicsforstudents.com. I've discarded it this year because I'm not getting enough time to write blogs. I'm good. I don't want to boast, but for my college, I write a lot of blogs. But here I'm not getting time. I'm writing blogs, taking classes, making videos, college works, webinars, audit. I mean to say, it is impossible. But I think that in near future, I will have a website, because I want to, include all those things what Salman is taking, a complete lesson, chapter 1, chapter 2, and so on. So I think that should be, but I don't know whether I will get a time. Anyway, chalo, take care, goodbye, and I will be back tomorrow. Is what, Friday? Yeah, Saturday I won't be in the live class because 8 o'clock onwards there will be a continuous webinar on general relativity, and Sunday also Dr. Debanjan Bose is coming on high energy physics, again coming from Monday. So keep an eye on the community box. If you don't want to connect through WhatsApp, I will share every new class. Bye bye. Yeah, Salman, bye bye. Every new class, every new time, if there is a change, I'm going somewhere, etc., is a change in time, I will share everything in the community tab and in my WhatsApp. I mean to say WhatsApp, what you call that picture which keeps on scrolling. I don't know what it's called. Okay, take care. Thank you very much for all of you for participating. It's really making things wonderful. Thank you very much. Bye, Dhruba. Bye, Physics Core, and bye, everybody. Take care.